All right, welcome everyone. Today we are talking about independence. Based on what we're doing in class today, I recommend trying the rest of the problems on homework 7 after class today. I will get homework 8 posted before class by Thursday, and when that is posted, this material will also be relevant for the first out-of-book problem on homework 8. Let's see, I started the recording, right? Yes. All right, so let's start off with a little bit of review. What does it mean for two events to be independent? We had 3 criteria. Can someone tell me one of them? Kyle?
Doesn't the probability have to add up to 1?
No, that would be if they are mutually exclusive and partition the space.
PA times PB equals to PA intersect PB.
Yeah, the probability of the intersection of A and B is the product of the probabilities of A and B separately. Sam, you got another criterion?
The probability of A given B is just the probability of A.
Right, probability of A given B is just the probability of A. So in other words, it doesn't matter whether or not B occurs, the probability of A stays the same. And we can have that same criterion, but with the events flipped. So the probability of B given A equals the probability of B. So these are our 3 criteria that tell us if events A and B are independent. And you can check any one of these. If one of them is true, then the other 2 will also be true. And if any one of them is false, the other 2 will also be false. So these are our criteria for events being independent. So now we have an idea of 2 random variables, x and y, being independent. So 2 random variables, x and y, are independent, if and only if the cumulative distribution function of x and y is equal to the product of the marginal cumulative distribution function of x times the marginal cumulative distribution function of y. If this is true for all values, little x and little y, that you could plug in. For discrete random variables, an alternative way we can check is if the probability of big X being equal to little x and big Y being equal to little y is equal to the product of the marginal probabilities for x and y, if that's true for all possible values, little x and little y. So this is the most similar to our 3rd criterion for events A and B being independent. 2 random variables are independent if this 3rd criterion works for all possible values, all the events of x and y taking on any of their possible values. So the event that big X equals little x and the event that big Y equals little y for all possible values of x and y. And for continuous random variables, we also have the alternative way to check that the density function, so the joint density function equals the product of the marginal density functions. So let's apply this idea to our committee problem. So we had our joint distribution function given here for the number of Republicans and number of Democrats on this subcommittee. And we want to know, are X and Y independent? So let's check this by checking our second criterion here for discrete random variables. So we'll start by finding the marginal distributions, like we did yesterday. So to find the marginal distribution of X, we're summing over all possible values of Y. So we're taking the sum of each column here. So the probability that X equals 0 is 3/15. The probability that X equals 1 is 9/15, and probability that X equals 2 is 3/15. And for our marginal distribution of Y, we're summing over all the possible values of X. So we're taking the row sums here. And then we want to check whether the joint probability of X and Y is always equal to the product of the marginal probabilities. So we have our joint probabilities, that's our upper table here. You can start by making an empty table with the marginal probabilities shown along the edges, and then just start taking the product of the probabilities in each row and each column. So for example, in this, where's my mouse go? Upper left-hand corner for X equal to 0, Y equal to 0, we would have 3/15 times 6/15. And right away, we see that that's not equal to the actual joint probability that X equals 0 and Y equals 0. So that means we can stop. We have found a value of X and Y for which the joint probability does not equal the product of the marginal probabilities. That's enough to say that these two random variables are not independent. Questions about this? All right. Now let's take an example with continuous random variables. So let's suppose we have the joint density function 6xy squared for x between 0 and 1 and y between 0 and 1. And we want to know whether x and y are independent. What do you think our first step is going to be?
Just be finding the, like the f sub x and x.
Yeah, find the marginal density function, f sub x and f sub y. So our strategy is going to be to find the marginal density functions and check if our joint density function that we were given, 6xy squared, is always equal to the product of the two marginal density functions. So our marginal density function for x is going to be the integral of our joint density function over all possible values of y. Remember, we're integrating over the other variable. And that turns out to be 2x. And the marginal density function for y, same thing, integral of the joint density function, but we're now integrating over the possible values of x. And that turns out to be 3y squared. So we found our marginal density functions. And now, if we take their product, 2x times 3y squared, that is 6xy squared, which is what we were given for our joint density function. So that tells us that yes, x and y are independent. So that problem is actually an example of a theorem, theorem 5.5 in Wackerly, that says let x and y be continuous random variables with joint density little f of x comma y that is positive when x is between two constants a and b, and when y is between two constants c and d. Then x and y are independent if and only if their joint density function can be written as a product of a non-negative function of x, call it g of x, times a non-negative function of y, h of y. So I'll give you a minute to get that written down, and then we'll look at some consequences of that. So for example, let's suppose that our joint density function is x plus y for x between 0 and 1 and y between 0 and 1. And we want to know, are x and y independent? So first, we look at the region where the density function is non-zero. So f of xy is non-zero between x between 0 and 1 and y between 0 and 1. So it's non-zero on a rectangle. So that means theorem 5.5 applies. We can use it to figure out whether these random variables are independent. But our density function is x plus y. It can't be written as a product of something involving x times something involving y. So that tells us that x and y are dependent or not independent. questions about this? Folks online, any questions so far? All right. All right. Two notes about theorem 5.5. One is that it doesn't apply if any of the bounds are positive or negative infinity. So A, B, C, and D need to be finite numbers. Oops. So if any of the bounds are infinite, then we don't know if X and Y are independent or not based on this theorem. In that case, you would need to solve it the other way by finding the marginal density functions, seeing if you can multiply them together. And this theorem also doesn't apply if the region where the density function is positive is non-rectangular. But if the density function is non-rectangular, meaning like it's only, the density function is only non-zero when y is greater than x, for example, then you should look for a place where the marginal density function is 0, like when y is less than x, but the joint density function is 0, like when y is less than x, but where the product of the marginal densities is not 0. Questions about that? All right. So for example, let's take our fast food restaurant example from yesterday. So we have the joint density function, e to the negative y, for our x being the amount of time you wait before placing your order, and y being the total amount of time until you get your food. And here our joint density function is non-zero when 0 is less than or equal to x, is less than or equal to y, is less than or equal to infinity. So just a note before we get into that, here, our region where the joint density function is non-zero is this like infinite triangle, right? Because y is greater than or equal to x, and x has to be greater than 0, but there's no upper bound on y. So we're looking at this region where our density function applies, where it's non-zero. So that means that theorem 5.5 isn't relevant here for figuring out whether x and y are independent. Agreed? All right. All right. So yesterday we found the marginal density functions for x is e to the negative x, and for y, the density is y times e to the negative y. Let's use these to find whether x and y are independent. And our clue is, because we have a non-rectangular support for our density function, so a non-rectangular region where the density function is non-zero, there's probably going to be a place where x is less than y, where this density function for our joint density doesn't apply, where the joint density is 0, but where we could multiply the marginal densities and get something that's not 0. So for example, let's take the density function at x equals 2 and y equals 1. And that's going to be 0 because it has x greater than y. So our joint density function here does not apply. But we can plug in x equals 2 and y equals 1 for our marginal densities and find that the marginal density of x at 2 is e to the negative 2, and marginal density of y at 1 is 1 times e to the negative 1. And then we can say, oh look, e to the negative 2 times e to the negative 1 is not 0. So x and y are dependent. Kyle.
Why couldn't we just initially say that the f of x times f of y doesn't equal to f of x, y?
So it's often easier to prove it by looking at a specific case. Like in this case, it's pretty obvious that when you multiply these, you're not going to always get e to the negative y. But in some cases, if you have a more complicated joint density function, it can be hard to see, oh, if I have to multiply these, that there's not some fancy algebraic way that I could make these two things equal. If you look at specific numbers, then you can actually compute both sides and show that they're different. Other questions about this example? All right. So now let's try an example where we use the idea of independence. So suppose a technician starts a job at time x, which is uniform between 8 and 8:15. And their time to complete the job is an independent random variable y, so it doesn't depend on what time they start, which is uniform between 20 and 30 minutes. And we want to find the probability that the job is done by 8:30. So take a moment to think about how you would approach this problem. All right. So far when we've been finding probabilities involving two random variables, we've always been given the joint density function. Here we weren't given that. We were given information about the distribution of x and separately information about the distribution of y. So we need to be able to put those together to make a joint distribution for x and y. And the fact that they're independent is what's going to let us do that. So we start out by using the fact that x and y are both uniform. So that tells us that our marginal density for x is 1/15 for x between 0 and 15. And our marginal density for y is 1/10 for y between 20 and 30. So then we can use the fact that x and y are independent to say that their joint density is going to be the product of their marginal densities. So we have 1/15 times 1/10. So we get a joint density of 1/150 for values of x between 0 and 15 and values of y between 20 and 30. All right, so now we want to use this joint density to find the probability that the job is done by 8:30. So we need to figure out what region to integrate this over. So our integral is going to look like this. We can do it as the bounds on x and the bounds on y for our two integrals. And then we're going to integrate our joint density function over those relevant values of x and y. Try sketching the region that satisfies the condition we're interested in. So the region that corresponds to the job being done by 8:30. All right, so if we want to be done by 8:30, that means that x plus y has to be less than 30. Agreed? So we can sketch the region where y is between 20 and 30, x is between 0 and 15, and then we have this additional constraint that we're interested in calculating the probability of x plus y is less than 30. Or in other words, y is less than 30 minus x. So that's this blue region here. Questions about this part? Sam? So the x-axis is the possible values for the random variable x, and the y-axis is the possible values for the random variable y. And then we're thinking about the density function as being a surface that lies above the xy plane. Does that help? Okay. All right, so try setting up the integral using this region. All right, so we could use either vertical or horizontal rectangles here. If we use vertical rectangles, then we'll have an order of integration dy dx, because we first integrate along the rectangle and then we think about moving our rectangle. So our line is y is less than 30 minus x. So our bounds for our inner integral would be from 20 up to 30 minus x. And our outer integral, so 20 is less than 30 minus x. So x is less than 10, because y can't be less than 20. So our bounds on x then would be from 0 up to 10. Questions about this? Folks online, questions? All right. So our inner integral, we get the antiderivative of 1 over 150 with respect to y is 1 over 150y. And we're evaluating that at 20 and 30 minus x. So that becomes 1 over 150 times the quantity 10 minus x. So then for our outer integral, we have the integral from 0 to 10 of 1 over 150 times the quantity 10 minus x. And just using the power rule for integration, we end up with 1/3. So there's a 1/3 probability that the technician finishes by 8:30. All right. So let's try another one like this. The amount of a loss due to a fire, so the amount of money that's lost because of the fire, has an exponential distribution with a mean of 2. And the proportion of the loss that's paid by insurance, so y is a proportion, it's between 0 and 1, has a beta distribution with alpha equal to 5 and beta equal to 1, independent of x. And we want to write an integral for the probability that the insurance payout in dollars is greater than 2. So give this a try, and then we'll talk about it. right, so first of all, how does the insurance payout in dollars relate to X and Y? So suppose that the amount of loss due to a fire was 2, and insurance paid for half of it. How much was the insurance payout? 1. How'd you get that?
Just 2 times that half, or half of 2.
Right. So by saying we want the probability that the insurance payout is greater than 2, we're saying that we're looking for the probability that X times Y is greater than 2. And remember that the way to find this probability, this X times Y is not going to be inside the integral. It's not going to be the integrand. The integrand is going to be our joint density function, f of x comma y. So then we'll use this x times y being greater than 2 to help us choose our bounds of integration. Go ahead and start by figuring out what the integrand should be, the joint density function. All right, so our marginal density function for x should be an exponential density function with a mean of 2. So we have 1/2 e to the negative x over 2 for values of x greater than 0. And our marginal density function for y should be a beta distribution with alpha equal to 5 and beta equal to 1. So we have gamma of 6 over gamma of 5 times gamma of 1 times y to the 4th times 1 minus y quantity to the 0 for values of y between 0 and 1. So then the joint density of x and y is going to be the product of these. So we have 5 factorial over 4 factorial. So the 4 factorial is going to cancel with the 4 times 3 times 2 in the numerator here. So we just have 5 times 1/2, so 5 halves, times e to the negative x over 2 times y to the 4th for values of x greater than 0 and y between 0 and 1. Questions about this part? All right, so now we have our integrand. Now we need to find our bounds of integration. And I really, really recommend sketching a region for this. So we're trying to find the probability that x times y is greater than 2. And we can rearrange that into the probability that y is greater than 2 over x. I often find it helpful to separate y on one side of the inequality, because thinking back to like high school, it's easier to think about lines and curves as y being a function of x. So then we can sketch the curve y equals 2 over x. That looks like this. So here's a height of 1 for y, and x on the x-axis, this is labeled from 2 to 8, but really x doesn't have an upper bound because it has an exponential distribution. It could be anything between 0 and infinity. So this solid black curve is y equals 2 over x. We also have the constraint that y has to be between 0 and 1. So I've also drawn this horizontal line at y equals 1 to know that we have to be below that. And then we can identify an example rectangle to help us do our integration. Here, vertical rectangles work much better because they can go from the curve 2 over x up to the line y equals 1. Questions about this diagram? Kyle?
Why do we put the red line in?
So drawing an example rectangle is helpful for figuring out whether you want to do your integral dy dx or dx dy. So you want to sketch an example rectangle so that you can define what curve it's going from and going to, and that those curves or lines are consistent no matter where we put that example rectangle. So we can imagine sliding this to the left, it would still be going between the same 2 curves, or sliding it to the right, it would still be going between the same curve and the same line. Does that answer your question? All right. So try writing the integral using this as our region with a vertical example rectangle. Can someone online tell us, if we're using vertical example rectangles, do we want dy dx or dx dy for our order of integration?
dy dx.
Exactly. We want to think about first integrating along the length of the rectangle, and then after that, sliding the rectangle along the region. So we'll do dy for our inner integral and dx for our outer integral. So then for our inner integral, the bounds for y, what should the lower bound for y be? 2 over x, because that's what we're trying to find the probability of. What's the upper bound for y? 1. And what's the lower bound for x if we think about our first rectangle, if we slid it as far as possible to the left? Yeah, that'd be 2, because that's where the curve y equals 2 over x has to intersect the line y equals 1. And you can see that on the graph, that x equals 2 is our leftmost point. And then what's our upper bound for x going to be? Yeah, it's infinity. All right. So that gives us this as our integral to find the probability that the amount in dollars paid out by insurance is greater than 2. Probably in real life, it wouldn't be in dollars, it'd be like in thousands of dollars. All right. Oops, and then I did not have a slide where we went through how to integrate that. Are there questions about this? Kyle.
So when we multiplied the two PDFs together,
Mm-hmm.
that was just, that gave us f of x of y, not f of x of y, but f of x y.
Right, so that gives us f of x comma y, that's the joint density function. And the reason we could do that was because the problem told us that x and y were independent.
Is it because they're continuous PDFs that we could say that they're f of x and y, because f of x of x, because yesterday we had to do it like a certain thing to get it like that. We had to take the integral, I think.
So yesterday, the problems all gave us the joint density function, and then we needed to find the marginal density functions. Here, the problem isn't telling us the joint density function. It's telling us, here's the distribution of x, it's exponential. Separately, here's the distribution of y, it's beta. So the problem is giving us separately information about the distributions of x and y. So those are the marginal densities. And then because they're independent, we can multiply them to get the joint density.
So we just say the marginal density function, we're not doing anything.
By telling us that x is exponential with mean 2, the problem is implicitly telling us that this is the marginal density function for x.
Okay.
Yep. Other questions about this? Folks online, any questions? All right. Thank you all for your attention. I will see you on Thursday for more practice with independence and conditional distributions.
Thank you, Doctor.